Hello everyone. Let's wait for 5 more minutes. Let's see if anyone joins. Then we'll start sharp at 3:05. Okay, so good afternoon everyone. Let's start. So this is NOC EE-62 NPTEL tutorial on basic electronics. The course is taken by Professor Mahesh P. Patil from IIT Bombay. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar, and this is a tutorial session mostly regarding the problem solving so that you can solve your assignments fluently. As you know, we are in the 7th week and we go live every week 3 to 5. So again, I will reiterate some prerequisites. I am expecting that you guys have at least gone through the lectures posted previous week and also attempted the assignments, right? Then it will serve the purpose. Uh, for to maintain some decorum, please mute your microphone all the time. And if you want to ask any question, use the raise hand option or you make comment, or you can, after the one problem or each topic has been discussed, you can unmute yourself and ask your questions, right? And also at near the end of 2 hours, we'll be given 10 minutes time to ask your general query regarding the session. Also, please keep a scientific calculator handy so that you can follow the calculation and all, right? The lecture link and all, I think you guys are well familiar by now where to find it. It is available on the course webpage on the live session, live problem solving session tab. There is a Google spreadsheet where you can find the folders of these presentation files and also the links of the channels where you can watch the videos, right? So this is week 7. Let's begin. Today we'll discuss mainly ideal op-amp circuits, right? Last week I have discussed what is op-amp, how we can go about analyzing ideal op-amp circuits, what are ideal op-amps, and some basic fundamentals on that, right? Today we'll be discussing a little bit of advanced topic, but we'll keep our focus on ideal op-amp, right? So let's begin. As for the first problem goes, it is asked that uh, a topology is given. So if a topology is given, the op-amp is said to be ideal and resistors are said to have a tolerance of plus minus 1%. That means this can vary plus minus 1%, right? Then they are asking us to find out the range of V naught. Okay. So few things. First, we will assume that the op-amp is ideal. Op-amp is ideal. And also for today, mainly all the circuits are in negative feedback, right? We will assume that. Last week I have discussed a very lucrative method to find out how you can check whether the op-amp is in negative feedback or not. So if you have missed that session, you can go back and check whether this all the circuits are in negative feedback or not, right? So we'll assume negative feedback. And what is the consequence of this? First, ideal op-amp means Rin is infinite. That means no base current, right? And also your intrinsic gain of the op-amp is infinite, right? So what is the consequence of these 2 points that the op-amp is ideal and the circuit is in negative feedback? Is that the these 2 ports, the input ports of the op-amp, can be assumed to be virtual short, right? Virtual short. So these concepts generally help us to analyze this op-amp, ideal op-amp circuits very easily, right? And if you are aware about this much, then it is just KCL and KVL, right? So again, this current, there is no current going inside in these 2 ports if the op-amp is ideal, right? So then we just have to use analyze KCL and KVL at this node, right? Or any node which is with the feedback. So that's all there it is. So first we'll discuss what do I mean by this, right? The tolerance of resistance is plus minus 1%. So I have R1 So R1 nominal, nominal means whatever is given is 1.2 kilo ohm, right? And R2, let's say R2, R2 is nominal 15 kilo ohm. Okay. So what will be the maximum R1? The maximum R1 will be nothing but this into 101%, right? Because 1% tolerance is there. So that means this come up to be 1.212 kilo ohm, right? Similarly, your R2 max is nothing but 15.15 kilo ohm, right? You can simply check this 15 cross 1.01, it should be 15.15. Similarly, your R2 minimum is nothing but 1.188 kilo ohm, and your R1 minimum, and your R2 minimum would be 14.85, right? So the tolerance means your resistance will vary between this range. Okay, so resistance will vary, both the resistance will vary between this range. So we need to find out how does this affect the output voltage, right? So they want us to find out what will be the range of the output voltage. So how can I do that? It is very simple. You just simply have to consider that as this node is 50 millivolt, so it is in virtual short because the op amp is ideal and it is in negative feedback. So this will be also 50 millivolt, right? So if you use KCL at this node, so you have 0 minus 50 millivolt over R1 is equal to 50 millivolt minus V0 by 15, right? So if you solve this, you will find out that this is V0 by 15 is nothing but 15 to, let's say not 15, let's say it's R2. We'll find out why I am writing it in R1 and R2 term, right? So it will be 1 over R1 plus 1 over R2. And this will also be R2. So now if you see, your V0 will be simply 50. This V0 by R2 comes this side and this comes this side. So 50 into 1 plus R2 by R1, right? This millivolt. R2 and R1, R2 by R1 ratio is unitless. So now you need to find out the range of V0. So your V0 will be V0 minimum when my this term is minimum. This term is minimum when my this term is minimum. So when my R2 by R1 is minimum, right? So how will that be minimum? When my R2 is minimum and my R1 is maximum, right? This is the lowest limit I will have on R1 R2 by R1. Okay. So what is that? R2 minimum by R1 maximum. R2 minimum we know it is 14.85 and R1 maximum I know that it is 1.212. So it is coming out to be 14.85 over 1.212 is nothing but 12.2524. Okay. So your V0 minimum is coming out to be 50 times 1 plus 12.2524 millivolt, and that is 662.62 millivolt, or you can say simply 0.66 millivolt, right? And what about your this? Similarly, I can write that your V0 will be V maximum when R2 by R1 will be minimum, and that is nothing but, sorry, R2 by R1 will be maximum, and that is nothing when the numerator is maximum and the denominator is minimum, right? And that is nothing but 15.15, and this was, if I am right, 1.188. Okay, so it is coming out to be 12.7525. Okay, so similarly you can find out V naught maximum as 50 of 1 plus 12.7525, and that will come out to be 687.6 millivolt, or simply you can say 0.69 millivolt, right? 69 volt. So your V naught will vary from 0.66 millivolt to 0.69 millivolt. What is the physical implication of this circuit? The physical implication is such that, suppose you want to make a non-inverting amplifier, as this, by the way, this topology is called non-inverting, right? So suppose you want to make a non-inverting amplifier, and you want to make, say, 10 number of such amplifiers, and you go to the store and you buy these resistances, right? These resistances, these have some color bands, and based on the last two bands you find out the tolerance on that. So if it is mentioned that there is 1% tolerance, right? So the resistance value will not be fixed actually. So it will vary over a certain limit. So you will be getting that how your output voltage will vary. And accordingly, you will design your next stages of the circuits, right? So this is why this kind of analysis are important. So the one request I want to make, that never mug up any circuits or any formulas, right? If you are fluent in solving KCL and KVL, you can just analyze any RC circuits, and you need to know about the basic elements only. So don't ever try to remember any formula. It will not help. So this is so V naught is okay. B is my right option, right? So let's move on to next problem. If you have any question, you can simply ask at this stage. Okay, so let's move on to problem number two. Problem number two tells us that in the integrated circuit shown in the figure, the input is 8 volt peak to peak, and it is of 1.2 kilohertz. Just hold on a minute. Okay, so we are back. It is mentioned that the input is 8 volt peak to peak and 1.2 kilohertz square wave. And in order to obtain a 4 volt peak to peak in output voltage, what is the value of R required, right? So what is my input voltage? My input voltage waveform is of the shape that it is like this, right? It is a periodic signal and it has 8 volt peak to peak. So I can safely assume that the DC level is at 0, and this is varying from -4 to +4 volt, right? So this is your V input, and this is your time axis. Okay. And what about the period of the waveform? Your period of the waveform is nothing but 1 over frequency, and that is 1 over 1200 seconds. Okay. So what is the period, by the way? Period is this much. Okay. So now what are they asking? They're asking us to, okay, first let us think about this. Suppose you have a signal, and you want to integrate it. You have a signal like this, and you want to pass it through an integrator, right? How will your output will look like? How will your output look like? Say this is your input and V naught T is your output. How will your output look like? V naught T is nothing but VIT, and it passes through a integrator, and we have V naught T. How will it look like? It will just it will be just nothing but a ramp, right? How this ramp is coming, by the way? If you want to visualize this, you can simply check that what is your this. Suppose, let me go over to this. Suppose you want to integrate this waveform, right? This left side waveform. What will you do? You want to take the area under the curve, right? That is integration, by the way. So your one axis is constant, another axis you are increasing t, so it will increase linearly, right? So at this point it has the maximum positive area, and as soon as it is crossing this point, the negative area starts to come, so the effective area will get reduced, so it is again going back with this slope, right? So again it will come back here, so your output waveform will look like these things I think you are aware of, and you must have done it in your signal systems course, right? You can use Laplace transform also to solve this. You can simply take your unit step as 1 by s in the Laplace domain, frequency domain, and you can just simply integrate it, right? You can simply do the multiplication, and then you can just reverse take the inverse Laplace transform. So that is one way to do it, but we'll keep it simple. So what do I found? Can you tell me whether the period of this signal is changing? The period is not changing, right? Because this remains my period of the signal. This remains my t. T remains 1 over 1200 second, right? And this is your 4 volt. This is your minus 4 volt. And what about this? This is 0 volt. So this also has a 4 volt amplitude, right? And this is peak to peak. Understand this very carefully. For the rectangular waveform, the peak to peak is this much. This is 8 volt. But for the triangular signal, the peak to peak is this, right? So 4 volt. So this is a cross validation that we have drawn the waveform in the right manner. See, this is 8 volt. This is 8 volt peak to peak for the input and 4 volt peak to peak for the output. This is what is desired. Okay. So now we'll analyze this circuit and see how the integration operation is happening, right? Let me copy the circuit. Okay. So again, we will assume that the device, the op-amp is ideal and it is in negative feedback. So this will be ground, and this will be ground, and what about then KCL at this node will be current coming in and current going out, right? At AC frequency, suppose another point I want to make here, that suppose you have a circuit like this, right? And you apply some AC signal. This is 50 nanofarad, and say this is of your omega is nothing but 2 pi into 1200, right? So what will be the impedance in this branch? What will be the impedance in this branch? It is nothing but, let's say this is X is 1 over j omega c. Okay. What is 1 over j omega c? This is 1 over j into 2 pi into 1200 into, what is this? This is 50 nanofarad, right? 50 into 10 to the power 9 minus 9. And what about this resistance? This is 150K. So if you solve this, you will find out that at your AC, this branch impedance is much lower than this 150K, right? So you can simply assume that your 150K is open circuited. So what your effective circuit will look like? Your circuit will look like simply this. This is your R, and this is the input signal you are playing, and this is your V, right? So how will I solve this circuit? I will just simply use KCL in this branch. Let's say this is I1, this is IC. So your I1 is nothing but V input minus, let's say this is V input minus 0. This point is 0 over R is equal to, what is this current? This current is nothing but C D voltage across this capacitor in this direction, that is 0 minus V naught over dt, right? C dV dt, the current across capacitor, current through the capacitor. If the voltage across the capacitor is V naught, is V, then it is C dV dt, right? So your VI over R will be C minus dV naught dt. Let me bring this to this side denominator. So your V naught would be nothing but 1 over RC, negative sign, and this is VIT dt. See why they are calling this circuit as an integrator? Because at the output you will get an integrated version of the input, right? So we know the nature of V of t. So how will we go about it? They have mentioned that your V naught t is 4 volt, right? Peak to peak. Now if I just copy this, say this. This is your, from this you can see simply V naught is 4 volt at this point, right? What is the total integrated part when V out t is 4 volt? It is nothing but this area, right? And what is this area? Let's say this is 1 over RC, and this area, let us take it in the modulus term, okay? And say your, this area would be 4 into this T by 2. What is T by 2? 1 over 2400, right? You see, this is T by 2, okay? So your R would be nothing but 1 over 600 into 4 into your 50 nanofarad, right? Minus 9. So your R would be 10 raised to 9 over 200 into 600. So 10 raised to 9 divided by 200 divided by 600. So your R is coming out to be ohm, right? So that is nothing but 8.33 K. So this is a very simple way to find out the resistance, right? You are free to try it out using the Laplace transform, and also you can solve this integration. This is nothing but a linear simple, you are integrating a constant, so you will get a t term is a linear term, right? You can just put the limits, but you can solve it from the graph also. So I have solved it in one approach. So I will suggest you to try to solve this using Laplace domain, also by performing the integration. Okay, so this is a very simple problem. So what is the moral of the story? That if you know your basics, you can solve this kind of problems very easily, right? So you even need not have to know whether this circuit is integrator or not, what is the formula for the op-amp integrator circuit. You just simply have to use your common sense and your basic circuit analysis technique to get the answer, right? So this would be your right answer, 8.33K. Okay. So you have any question? I will be happy to answer. Else I will move on. Okay. So let's move on. Let's move on to problem number 3. So what it is telling that consider the integrator shown in the figure. The input voltage is a 5-volt peak-to-peak square wave with frequency in the range of this to this. We want to be able to adjust the output voltage to be 5-volt peak-to-peak for any frequency of the above range. Okay, simply you have this formula. Okay, it is the same circuit. You know this much. What is this? This is nothing but V naught, right? What is this? This is nothing but V input peak to peak by 2, or simply you can say it V peak, right? And this was your 1 over 2 into frequency, right? You can simply use this formula only, right? So what they are asking, when your frequency is 1 kilohertz, right? What is your V naught? V naught is your 5. Your R you do not know. C you know it is to be 50 nanofarad. What is your V input by 2? It is 2.5, because this is also peak to peak, input voltage 5 volt, and this is also peak to peak, right? So this is your 2.5 into 1 over 2 into 1000, right? So 2000. So what will be your R? Your R will be nothing but 2.5 into 10 to the power 9 divided by, you have here 5, you have here 2000, and you have the 50, right? So this 10 to the power 9 I have taken from 50 nanofarad, that nano part on the numerator side. So you will have this divided by 5 divided by 2000 divided by 50. So you have 5000, right? Or 5K. Again, for f equal to 2 kilohertz, see the range of the frequency in the question, 1K to 2K. So if equal to 2 kilohertz, it will be nothing but this term will be multiplied by 2. So 5 kilohertz, 5 kilo ohm will be divided by 2, right? So it will be 2.5 kilo ohm. For this, your R will be 2.5 kilo ohm, right? That means if your F is from 1 kilohertz to 2 kilohertz, your R would be from 2.5K to 5 kilo ohm, right? So your this is corresponding to this and this is corresponding to this. What does that mean? That your frequency is proportional to 1 over R, which also we know that if your C is constant, you can check the dimensional analysis also, right? So F equal to 1 over RC from the dimension point. Let me just from dimension point of view, this is right. If this is constant, then your F should be proportional to 1 over R. Okay. So if we, as we see that your frequency is increasing to get the same output level or to have the same, I would say, charging constant, you would have your resistance would be divided by 2, right? This is multiplied by 2, so this would be divided by 2. So it is pretty simple, right? So this is how your correct answer would be your B. So this is how you find out this kind of answer to this kind of problems. Okay. So let's move on to next problem. Okay. Okay. So let's move on to problem number 4. For the circuit shown in the figure to work as a difference amplifier, what value of R is required? So now say you do not know anything about difference amplifier. Okay. I will tell you what difference amplifier is. Difference amplifier is nothing but which uh, takes the difference of the input, and suppose you have two kind of input Vi1 and Vi2. So what will be your difference amplifier? This will be nothing but in this form. This is your gain, and gain terms this. So it will first take the difference and then amplify it. Okay, this is the definition of difference amplifier. So now you say you do not know anything about difference amplifier and you want to solve this circuit. How will you go about it? The very basic way to go about it is, you know that the circuit will be in, for it to act as a amplifier as a stable amplifier, it should be in negative feedback, and you are dealing with the ideal op-amp, right? So your virtual short condition still valid. So what will be your voltage at this point? At this node, your voltage would be Vi2 into R over R plus 1, right? This is simple voltage division. Simple voltage division because no current is going inside to the base of the positive terminal. Why it is so? Because we see a infinite input impedance at the base. So this, and this potential will also be same, right? So now if you apply, let's say this is your Vx, okay, Vx, this potential or this potential, this with respect to ground. So now if you apply KCL at this node, so this is your Vx. So KCL at this node, what will you found? Vi1 minus Vx over 2.2, right, is equal to Vx minus V0 over 33, right? So your Vi1 over 2.2 minus Vx 1 over 2.2 plus 1 over 33 equal to minus V0 by 33. Okay. So now if you see, you just simply substitute Vx, it will be Vi2 into R by R plus 1 into this will be your 35.2 over 33 into 2.2 will be minus V0 by 33, right? So this to act as a difference amplifier, you should have it in this form, right? Equal to V naught, right? So from this, if I simplify it further, V naught is equal V naught by say minus V naught is equal to 33 over 2.2. Now if you take common, it is Vi1 minus Vi2 into R by R plus 1 into 35 over 2 by 33, right? This is multiplying on the other side, 33. So now if you see V naught is equal to 33 over 2.2 Vi2 into R by R plus 1 into 35.2 over 33 minus Vi1. Okay, so this term has to be 1 to have the ideal difference amplifier, because the difference of the input should be amplified, right? I do not want one input to get some, it gets fractioned and then get substituted from the other, right? So how will you calculate your R? Your R over R plus 1 would be, so if you solve this, you will find out your R to be 15 kilo ohm, right? And what about the gain of the differential amplifier? Alpha. This is your alpha, right? So your gain of the difference amplifier would be 33 over 2.2. That is nothing but 15. Okay. So what was the question, by the way? The question was to find out the value of R. So R would be your 15 kilo ohm, right? So this is one way to solve the circuit. Another way to solve difference amplifier circuits, once you know this much and you have derived it in detail, so you can simply by looking at the circuit. Okay, just give me a minute. And this is Vx. Okay, so just let me. Okay. Another way to solve this problem is you see the ratio of the resistances, right? One thing you are sure that path will be determining your this path will be determining your gain of the amplifier, right? So if say this is R2 and this is R1, let me call it method 2. Okay. So your gain of DFAM would be, and let's see, this is R3 and this is R3 and this is R4, say. Gain of the DFAM will be R4 over R3 or R2 over R1. And what about the resistance ratio? The resistance ratio will be your R4 over R3 should be equal to R2 over R1. This condition has to be satisfied. So you see, you have 33. You know what did I need to find out? I needed to find out this R4, right? So your R4 would be nothing but R3 into R2 over R1, right? So what was your R3? Your R3 was 1K into what is your R2 by R1? Is nothing but 32 over 2.2. So it will come out to be 15. Okay. So this is a simple method to find out for ideal difference amplifier circuits. Now, why don't I recommend this method? Because you see, even if certain modification in the circuit, right, it may lose that it is a difference amplifier. One thing is that, and then you may confuse just by looking at the topology of the circuit, and if even if there is no symmetry in the resistances, which we will see in another problem later. Even if there is no symmetry in the resistances, then it will not remain a ideal difference amplifier, right? So then you may come to make the same mistake by using by simple these formulas. So it is suggested you always use method 1 to analyze the circuit because it is just involving KCL and KVL. So so far so good. Let's move to problem number 5. So problem number 5 is telling us about a it is looking like an difference amplifier, an improved difference amplifier. So can you tell me what is the just okay, first let me solve this circuit, then I'll tell something more about this circuit. Okay, that will be better. So what they're asking that a differential input of 10 millivolt peak to peak, that means your Vi1 minus Vi2 is 10 millivolt peak to peak. Okay, is applied to the circuit shown in the figure. So what is V naught? They want us to find out. What do we see? If we see the circuit very carefully, we can see a difference amplifier sitting here. Right? Can you see it? The ratio of the resistances are same. Right? So now if I just simply just simply let me draw this circuit again. Okay, the circuit looks like this. So this is your 10K, this is 22K, this is 22K, this is 10K, and this is 9.1, 9.1, and this is 0.22. This is your VI1, this is your VI2. Okay. Now let me mark these nodes. Let's say this is V1 and this is V2. Okay. So I will analyze the circuit in two parts. Why do I need to analyze the circuit in two parts? The matter of the fact is that simply because I see that this is a difference amplifier which I have just encountered. And the gain I can simply tell that this alpha would be 22 over 10, right? 2.2. This is coming from this circuit, and this one, the right hand part of this circuit are the same. Okay. So now let me start analyzing the circuit. So one thing is that I will just make sure that, okay, let's assume that this voltage is Vx, okay, and eventually it is in negative feedback, and the op-amp is in op-amp is an ideal op-amp, so the virtual short condition will be valid. So your, if I apply KCL at this node, KCL will be V2 minus Vx over 10 will be equal to Vx over 22, right? And in the above node, this node, KCL would be V1 minus Vx over 10 is equal to Vx minus, this is your V0, Vx minus V0 by 22, right? So if I just this is, let's say, equation A, this is, let's say, equation B. So how to go about solving this? You notice that it is a difference amplifier, so your V0 will be of the form function of V2 minus V1, right? So by looking at these two equations, I am just subtract equation B from equation A. Okay. So what will I get? I will get V2 minus V1 over 10. This will cancel, and this will be equal to, this will also cancel. So minus V0 over 22. Okay. So your V0 will be, this will be negated. So this will be plus. So V0 will be 2.2 into V2 minus V1. Okay. This is a validation that gain of this stage is 2.2, right? This is what we have, by inspection we could have said this. Okay, so then how to go about this? The input side of the circuit, you note that this voltage and this voltage, this is plus, so here virtual short will also be valid, so this is also, this is V2. Okay, this is V2, this is your V2, so this will also be V2. This is just connected directly here, so this is my V2. Similarly, this is V1. Virtual short will be there because this is connected through negative feedback and the op-amp is ideal. This point I am reiterating every time because to make sure that you keep in mind, these are the essential condition for virtual short consideration. This we have discussed in detail in last session. So you have, this is Vi1, this is Vi2, right? Now I need to find out this as a function of Vi2 Vi2 minus Vi1 or vice versa. So I have this, I have this. So I need to find out now V2 minus V1 in terms of Vi2 minus Vi1, right? Then my problem is solved. Okay. So now if I apply KCL at these two nodes, right? First on the top node, if I apply KCL, I see that there is no current in this branch, also no current in this branch. Okay, so just like for clarity, just, okay, just let me copy this much. I will draw it. That will be better. This is your V1, this is your V2, this is VI2, this is VI1, right? So your this node is also VI1, this is VI2. Okay. So now I am applying KCL at this node. So what will be VI1 minus VI2 over this was 0.22 and this was 0.22, this was 9.1, this was 9.1. Okay. So Vi1 minus Vi2, this current will be equal to current coming here. So Vi1 minus Vi2 by 0.22 will be equal to your V1 minus Vi1 over V1 minus Vi1 over 9.1, and KCL at this node will give me Vi2 minus V2 over, okay, just let me take it to this side, over 9.1 will be equal to this current is coming this current, so this will be Vi1 minus Vi2 over this, right, 0.22. So your again check the sanctity of the KVL, that Vi1 this minus Vi2 this current is equal to this input current, because no current is going here also, no current is going here also, right? Similarly, no current here, no current here. So this current also Vi1 minus Vi2 over 2.22 will be same as Vi2 minus V2 by 9.1. Let's say this is node B, this is node A. So this is node A, this is node B. Okay. So what I can see that this, if I just I can see this is equal to this, so I can just simply equate them. So V1 minus Vi1 over, and this you will find out to be, okay, just you want to find out the difference, right, of Vi1 minus Vi2. So why don't I just add these two? If I add these two, this becomes 0.11 times Vi1 minus Vi2 over, okay, this already is taken care of, will be V1 minus V2 over 9.1, and this will be simply, if you add this, Vi2 minus Vi1 over 9.1. Just cross check with me whether if I am doing any calculation error, just let me know, point it out. Okay, so this is V1 minus V2 by 9.1 and this is this minus this, so this will be minus, then I can write this Vi1 minus Vi2. So if I take it this side, so it will be Vi1 minus Vi2 into 1 by 0.11 plus 1 over 9.1 equal to V1 minus V2 over 9.1. What was my V1 over V2? Sorry, V1 minus V2, Vi1 minus Vi2 is, it will be nothing but 9.21 over 9.1 into 0.11 will be equal to, simply this is minus P naught over 2.2 into 9.1. Okay, so your 9.1 9.1 gets cancelled, so your V naught will be minus of this 2.2 into 9.21 over 0.11. That is coming out to be minus 184. This times your PI1 minus PI2. So it is plus 184.2 times Vi2 minus Vi1. Okay. So what you are finding that the gain is excuse me. So this is said to be 10 millivolt peak to peak. So you can see that your V naught will be 1.842 volt, right? So your correct answer would be your C. Now you can see that in this case we have again a difference amplifier, right? The in difference of the input, this is the difference. The difference of the input is getting multiplied by some alpha and giving me V naught. It is a more complicated circuit than this earlier case, right? Here also we are having the same thing. We are having, this is also a difference amplifier, right? Some difference of the input and then it is amplified to get some output. So can you tell me what is the advantage of using this two-stage circuit? If you can unmute yourself and tell me that why do I need to use this kind of topology? Anyone? Gautam Kumar or Subir Kumar Saha? You can unmute and tell me if you, what do you think actually? Why do we need this kind of circuit? Okay, so let me tell you why do we need. One thing you can see that the input impedance, looking at the nodes, here are infinity, right? Presenting idealness of the, our input is infinity at all the terminals. Idealness of the op-amp. Here you see you do not have input impedance of infinite, right? And why input impedance of infinity is of importance to us? Because we do not want any loading effect when I connect any circuit as an input stage to this circuit, right? This circuit should not load the previous stage. That's why we need infinite input impedance, right? So this circuit provides you infinite input impedance. That is one advantage. Another advantage over the previous one is that here you can play with four resistances, right? You see this, four resistances. You can play to tune your gain, right? This gives you more flexibility, right? So these are the two major advantages of using this amplifier, improved difference amplifier, right? So okay, moving on to the next problem. Just let me here. Okay, so in the circuit shown in the figure, what is the value of R required to obtain a gain with 50, right? The same analysis will be followed, but here simply I need that R will be required additionally, right? So again, the gain of this stage is 2.2. Now you can tell it by inspection only. So we can see that from the last time, I can simply just copy this formula and change the values accordingly, right? Or let me just copy this formula, this stage. So earlier case, this was 2 into R, right? Sorry, this was 2 by R. Okay. In the same, this is my V1, this is V2. In the same analysis, if you follow and if you do the same man, if you do the analysis in the same manner, you will find out this formula. So how does this is your R basically, right? So this R was getting multiplied by 2 if you add this 2, right? So this was coming out to be 2 by R. The same analysis we are doing here. So I am just avoiding the previous steps and I'm just showing you how you can go about solving this problem. So again, Vi1 minus Vi2, you would be 2 over R plus 1 over 9.1. And what is your V1 minus V2? Your V1 minus V2 was minus V naught by 2.2, right? Minus V naught by 2.2. Okay, into 1.91. So what they want us to find out? They want us to find out the gain. This should be your V naught by V1 minus V2 is nothing but 9.1 into 2.2 into your this term, right? There is a negative term. Okay. So let me take the modulus only. Okay. So this is said to be 50. 9.1, 2.2, 2 by R plus 1 over 9.1. So if you solve it, 50 over 9.1 over 2.2 minus 1 over 9.1, I answer into 2, right? So it will find, you will find it to be 837, 0.837. Obviously it is in kilo ohm. So you can simply say your R will be 840 ohms. Right? So same analysis, you do it in the same way. Consider the output difference stage first because you know how to solve that. And then you come back to the input stage. Use KCL at this node, or you may use at this node and this node also. And then you find out by simply adding and subtracting this circuit. Consider, you remember that this is a difference amplifier, right? So you have to anyhow make it a difference of two terms. That is the manipulation of algebra only, how you solve this circuits. Okay, so this should not be any problem. So this is as far as question number 6. So let's move to question number 7. Again, this extra page is coming. Okay. So question number 7 is asking in the difference amplifier shown in the figure, R1 is 1% larger than nominal value, while all the other resistances are equal to their respective nominal values. What is the common mode gain of the amplifier? So first of all, let us understand what is meant by common mode. Okay. If you take any signal, right, let's say I take a signal like this. Okay, so I can break it as an odd and even part. Any signal can be break into a sum of can be broken into a sum of odd and even signal, right? So it will have your, let's say, V common plus V difference by 2, or you can say simply V common plus V difference by 2 plus V common minus V difference by 2 should be. Okay, so you see that, or let me put it in this way. Uh, if you take any signal, it has some even part and odd part in common. You can split the signal into even and odd part, and you will find out that your signal has some common part and some differential part. Okay, so differential part would be the part which is of opposite sign, right? And the common part would be which is of the same sign. So now if you are designing a difference amplifier or a differential amplifier on op-amp, the idea is that you want the difference to get amplified, right? So suppose you have this Vi1 and Vi2, right? Suppose you have Vi1 equal to Vc plus some Vd1, and Vi2 has similarly Vc plus some Vd2. Okay, so you want this part not to get amplified. Okay, so your input would be basically this is your Vx1 say, and this is Vx2. So basically your V out should be of the form alpha of Vd1 minus Vd2, right? This you should have, and V naught should be Vc minus Vc should be equal to 0. So your common mode gain should be ideally 0, and your differential gain is what you want. Okay, so now if you think it in this way, how do you analyze a common mode circuit? Common mode means you apply the same voltage at the input. You just short two input terminals and apply the same voltage and see how your circuit behaves. And this gain should be very close to 0, because you want the difference of the two signal to get amplified, right? That is the purpose of your difference amplifier. So how to analyze this circuit? There is a hint provided that this should be 1. Okay, you can assume any constant input. You can assume, you can short the circuit and assume Vc. Then you need to find out the gain as V naught by Vc. If you just connect it like this, Vc, right? Then this would be your gain. But they are hinting that you take Vc equal to 1, so that if you calculate your V naught, it will itself be the gain. Okay. So we'll follow whatever they have suggested us in the question, right? So now tell me one thing. This is R1, R2, R3, R4, Vi1, Vi2. Now, if I apply 1 volt at both the input and my R2 over R1 is equal to R4 over R3. Whatever was the sign, it can take any sign, but you have to have it negative feedback, so it should be minus. So if this condition is true, then what is my V naught? Can anyone tell me if this condition is true? Let's say this is 2, this is 1, or let's say what, take whatever the value they have given, 20 and 20K, 1.2K, it is 20K, it is 1.2K. Okay, then what would be my V naught? Anybody? See, it is a difference amplifier, right? If it is a difference amplifier, so we have already analyzed this kind of circuits. So if this is the case, what will be the nature of my output? The nature will be of some constant terms into Vi1 minus Vi2, right? Now, if this difference amplifier is ideal, means this ratio is maintained, then what would be my V naught? My V naught would be nothing but the gain. What is the gain? We have calculated it to be 20 over 1.2, right? Into your 1 minus 1. Vi1 and Vi2 are same. That means your V out should be 0. That means your gain is 0, right? So your common mode gain is 0. So why did in the question they asked us to find out common mode? See, if you read the question carefully, they have asked that in the difference amplifier shown in the figure, R1 is 1% larger than its nominal value, while all other resistances are equal to their respective nominal values. What does that mean? That means that my this condition is no more valid, right? So I will not have this formula valid, right? That means I will not have zero gain. I will have some gain of very small or some value, but it will not be zero because my this condition is getting violated. This condition is getting violated in the question. Okay, so let us see how to go about this. They have asked us that R1 is 1% larger, right? So if my R1 is 1% larger, so my circuit would be this is 1.2, this is 20, this is 1, this is 1, this is 1. This will be 1.212, right? 1% larger, and this would be my 20K. So what is this voltage? Voltage at this node? It is, let's say, Vx. So Vx will be 20 over 21.2, right? Into 1. It is simple voltage division. So what is your 20 over 21.2 is nothing but 0.94339. Okay, let's take this value. So this voltage is also same Vx. So your 1 minus Vx over 1.212. Now I am applying KCL at this node. KCL at this node. So 1 minus Vx over this is Vx minus V naught over 20, right? So this, if you substitute Vx, 1 minus 0.94339 over 1.212 minus V naught over 20. So what will you get? 1 minus answer divided by 1.212 into 20.9439. So you will get your V naught to be 9.334 into 10 raised to minus 3. Right? So this is your this volt. What was your input? Your input was 1, right? So this itself is the gain. So what is your common mode gain? Your common mode gate is simply nothing but 0.009334. Okay. So if you see that this is your right option, right? This is how you find out the common mode gain. So moving on to the next problem. Again, the same circuit is given. Now they have mentioned that your R2 is larger, right? So again, if I will redraw the circuit, so this I would say here I am applying 1 volt. Okay. Now this is my 20K. This is my 1.2K. This is 1.2K. But this now is 20.2K. Okay, 1% larger. So how will I go about solving this? Again, this is Vx. Vs remains same as of the last problem. So 0.94339. See, I am dealing with a very small value, right? If I see the option, it is in the milli range. So that's why I am taking this value a very large, very high precision, right? For multiple decimals, because I need to get the difference so that the difference is, see, if you see, you might have a question that why do I need to take this much decimals? I see the answer here is in third decimal. So at least I should take two more decimals precision, two more precision value, right? So that's how I was sure that how to take this high precision decimal value. Otherwise, I was simply could write 0.9. So 0.9 will not serve any purpose, right? 0.9, 0.91 if I write it as 0.9 and 0.92 if I write it as 0.9, then the difference, even if it is 0.01, you will see it as to be 0. So that will not solve the purpose, right? So if this is my Vx, so again 1 minus Vx over, let me directly write this, 0.94339 over 1.2 is equal to 0.94339 minus V naught over 20, right? So 1 minus 0.94339 divide 1.2 into 20. So this would be 20.2, right? 20.2. Okay, so this minus, you'd have, did I make some mistake at some point? Your Vx is 0.94339, right? 1 minus this divided by this, so 0.94339 minus your answer. Your V naught is coming out to be minus 9.545 into 10 raised to minus 3, right? So your gain V in is 1. This is your V in. So your gain is minus common mode gain alpha C. Common mode gain is your 0.009545. So your right option would be this. Okay. This is how solve this kind of problems. Now again question number 9. Now what are they telling? They're telling the R3 is larger, right? 1.212. So again, simply if I check my Vx will now change. Vx will be 20 over 21.212 into 1, you can say. I will just apply 1 volt common voltage at the input. So 20.212, 20, sorry, 20 divided 21.212 would be your 0.94286, right? So again, your this will be 1 minus 94286 by 1.2 is equal to 0.94286 minus V naught over 20 0.94286. Answer would be your V naught is coming out to be minus 9.43115 into 10 raised to minus 3. That means your alpha C would be minus 0.00943175. Okay, so this is coming out to be this one, right? Similarly, this I will not solve. This is for your R2. That means you take this as 20.2K. So similar method you can solve. Similar way you can solve. Okay, find out Vx, then again assume virtual short, and then to consider KCL on the upper side, upper loop, and then upper node, and then you can simply find it out. So your alpha C will come out to be 0.0094. Okay, so this is do it yourself. So let's move on to problem number 11. So they want us to find out, this is the same problem. See, same circuit is given. If the same circuit is given and your R1 is larger, then you know your common mode gain alpha C is, what was your common mode gain? It was this one, right? 0.009334. Or simply let me take the whatever the value written in the answer, right? 3. Just let me take this much. Okay, this was your common mode gain. Can you tell me the differential gain? Anyone? We have discussed this kind of circuit today several times. Can anyone please unmute and tell me what will be alpha D just by looking at the circuit? Okay, if you are not getting it or if you have guessed it rightly, It would be nothing but ratio of these two resistance. Why? Because this is a ideal difference it is an ideal difference amplifier, right? So this would be nothing but your R2 by R1, right? So even if your R1 is larger than nominal 1%, it will not have that much effect on your differential gain, right? So this you can simply write out to be 20 over 1.2, 16.67. Okay. Okay. So what is your CMRR? What is CMRR, by the way? It is nothing but common mode rejection ratio, right? And it is defined as alpha D over alpha C. So in this case, it is 0.0093. It is nothing but 1792. Around it is 1792. Now they want us to find the answer in dB, right? So this is nothing but a voltage gain. So what is the formula of dB? So let me write it in this way. CMRR in dB is equal to nothing but 20 log base 10 into C of CMRR, right? That is 20 log 10 of 1792. So log sir into 20, it will come out to be 65.067 dB. Okay, so your answer would be C. Now regarding dB, I want to warn you regarding one thing, some definitions regarding dB, decibel. Decibel. Okay, so suppose you have a ratio A2 over A1. Let's say it is a voltage gain, not A2 over A1, V2 over V1. Okay, so what will be it in dB? Your dB it will be 20 log V2 over V1. Okay, now if it is a power ratio, then what is dB? dB is nothing but 10 log 10 P2 over P1. These are the same thing. How? Now say if your P2 is V2 square by R and your P1 is say V1 square by R. See, this is power only, right? If the voltage across the resistance R is in one case V2, in another case V1, then the power will be V2 square by R and V1 square by R. So what is your dB then? dB will be 10 log 10 V2 square by R by V1 square by R. So it will be 10 log 10 V2 by V1 whole square. We know that we can bring down the power. So this will be nothing but your V2 over V1. Okay. So when you deal with any kind of ratio, you should always check whether it is a power ratio or a voltage ratio, right? If it is a power ratio, then you go for 10 log base 10 of that quantity, unitless quantity. Okay. Now, let me tell you another thing, that there is something called dBm, right? dBm. dBm is nothing but a, it is not a unitless quantity, right? It is a, I can tell you that it is to define certain level of power. Okay. And what is the definition? Your dBm is 10 log 10 power divided by 1 milliwatt. Okay. So what is 1 milliwatt power in dBm? 1 milliwatt power, if I put P equal to 1 milliwatt, then it is log 1, and log 1 is 0, right? You see the how is the log plot? This is log x, this is x. Let's say this is 1. So your log plot is like this, right? It is asymptotically reaches 0 when it is infinite. So basically, note here that log 1 is 0 and your log 0 is minus infinity, right? How does this come? Because let's say the base is 10, we know that 10 to the power 0 is 1, and we know that 10 to the power minus infinity is 0, right? This is how these definitions are coming. So if your P is 1 milliwatt, then your that is called 0 dBm power. Okay. So now can you tell me if it is say 10 milliwatt power? 10 milliwatt power would be log 10, it will be 1, right? So it will be like 10 dBm power. If it is 10, you can simply see if P is equal to 10 milliwatt, then log 10, 10 by 1, this is milliwatt, so it will be log 10 base 10, right? It is 1, and there is a multiplication factor of 10, right? So 10 dBm. So whenever you find out the unit dBm, this defines certain level of power with respect to 1 milliwatt power. Okay, this you keep in mind. So whenever you say somebody tells you that this is 1 dBm power or 0 dBm power, you can immediately switch it back that 0 dBm power means they want us to consider 1 milliwatt of power. Okay, so this you keep in mind. This dBm and dB are not same. Remember that. This is dB and this is dBm. Okay, so that's what for dBs. And now let's move on to problem number 12, right? Okay, so the op-amp circuit in the figure is ideal except for an offset voltage of 5 millivolt. So what is an offset voltage? See, these op-amp circuits are not so trivial, you know. These op-amp circuits may look so simple, but it is actually made of some differential amplifiers, right? So using some BJTs and MOSFETs. So let me first show you one document. This is This is a two-stage differential amplifier which I designed, I think last year. So you see, uh, just let me tell you what it is. This you can see, this is the current source biasing. Okay, this I am telling you as a op-amp inside. Okay, op-amp inside. If you open down a op-amp or crack open an op-amp, so you will see that this kind of circuitry are there in inside the op-amp. Okay, so whatever we analyze the ideal op-amp, that is just very basic abstract. Okay, so this is your biasing network. Now this is your first stage. This is your first stage of deep amp, and this is your second stage, right? This and this. There are so many other things to improve the circuits, like these capacitance resistances. This you might have heard of Miller compensation or Miller effect. So you will learn this in later courses. So the basic purpose, this is the second stage. And you can build upon stages, you can build upon third stage, fourth stage, but that introduces certain poles and zeros which degrade the circuit performance. But obviously you need to trade something off for other. The main purpose of this is, if you focus on the this part, right? If you focus on the main first stage, you see that differential amplifier op amps are symmetrical, right? You see, here I have a PMOS. You can assume it as a some resistance. You just assume it some RC, okay? Some RC you say, and this is your main transistor. You assume it at a BJT. Just don't need to go here for MOSFET. Just assume it as BJT, okay? So what is happening for a differential amplifier is that uh, you see, for a difference amplifier, the ratio of the output impedances had to be same. But inside the that also, this transistors has to be or rather these transistors have to be perfectly matched, okay, to get the difference operation, and that will help us to have the common mode ratio 0. Okay, so these two strands basically, if let me this just okay. Okay, just let me tell this side strand. Okay, this left side, uh, where it is. Okay, this side strand and this side strand. Okay, these two branches has to be identically same. For left hand side should be equal to right hand side, but it is not always the case. Right? These things are made of semiconductors, be it BJT or be it MOSFET, and there are some process by which you can make these transistors. You might have heard of photolithography and all. So it is not always possible to make a perfectly matched transistor. Okay. So how do that mismatch been taken care of? That due to that mismatch, what happens? There you can translate it to or input refer it to at the input side of the voltage. Okay, these are the let's say mm, these are the, let's say, input side of the voltage. Okay, this, let's say, this is the input side of the voltage, so you can translate it back to the input and consider it as a differential voltage between the two input terminals. Okay, so now if I go back to this circuit, So how you can take care of this offset voltage? You can simply assume a voltage difference between these two nodes. You can simply assume a voltage difference between these two nodes. Or I would say that your virtual short is no more in place. Okay. This is called real device effects, real circuit effects, And this is when you go to the real world, this kind of effects you will not be able to consider this virtual shorts always, right? So how will you take care of this? How will you analyze this circuit? For this course, you analyze this circuit as, say, this is your, and also this the polarity of the voltage is not always fixed. The positive terminal may be 5 volt up to the negative terminal, or the negative terminal is sometimes up to 5 volts to the positive terminal. So how do you take care of this? You use this kind of symbols. Let's say, so here you see I did not use any polarity, right? But again, you have, for circuit analysis, you have to use some polarity also sometimes. So this is how you use, this means this can be plus minus also, or this can be minus, this can be plus also. Okay, because we do not know about the polarity, how the mismatch is going to be. So how do I consider this? Let me, for the sake of this, use a this condition, minus plus 5 volt, oh, 5 millivolt. Okay, and you have a resistance. Let me this. You have a resistance here. You have a resistance here, and you have a resistance here. 1K. This is 20K. This is 1.8K, and this is grounded. This is grounded. So you see, you will eventually have a operation of differential nature because you have some input voltage difference, right? Even though your inputs, your terminals are grounded after all, but you have a difference voltage due to the offset or the mismatch in the two pairs of the differential amplifier. You have a mismatch, and that is translated as an offset voltage at the input between two terminals. So how will you analyze these circuits? You This is your ground, right? So this potential is minus plus 5 volt, 5 millivolt. Again, we use the same circuit analysis technique, KCL at this node. So 0 minus this by 1.8 is equal to minus plus 5 millivolt minus V naught by 20, right? So if I take it this side, so, or if I take this to that side, so V naught will be 20 minus plus 5 millivolt by 20 plus minus plus 5 millivolt by 1.8. Okay. So your V naught would be nothing but minus plus 5 millivolt if I take it common, 1 plus 20 by 1.8. If you calculate it, it will come out to be plus minus or minus plus, what you can say, 61 millivolt. Okay, so this would be your correct answer. So in this way you can uh, take care of the mismatch and also take care of how you can solve about this what I say, offset voltage, right? So again, for the next circuit, another kind of real device effects or real circuit effects would be, you input bias current is not zero, right? What do you mean by input bias current is not zero? If you remember that we have considered for an ideal op-amp, the input resistance is infinite, right? If the input resistance is infinite, so my current going into that node would be zero, right? Because it's an open circuit. But in real device, as you know from your BJT analysis earlier, that at this input terminals, it is nothing but looking at the base of the BJT or the gate of the MOSFET. The gate of the MOSFET maybe have isolated complete isolation, but the gate of BJT will have some base current which is actually taking care of the all the operation, because my base current is the controlling element in the BJT circuits. So base current cannot be zero always, right? It is an basically I would say it is an invalid assumption to begin with. But for ideal circuit analysis, we assume that for op-amp, right? So you see, so you have, if I zoom it up, so you see these currents, what I was earlier taking as to be zero, now I cannot take it to be zero, right? So now let me take it I1 and I2. Okay. I1 and I2 can be interchangeable. Okay. Means your I1 may be flowing to a plus terminal or I2 may be flowing to minus terminal, just like the offset voltage polarity. So how it is defined, the half of your I1 plus your I2 is generally IB, 80 nanoampere given. Okay. So what about your this offset current? Offset means the difference of these two. This I1 minus I2 is to be 50 nanoampere, right? This is given in the question. But I am not, so I1 and I2 you will get two values from these equations. But what I am telling that I1 and I1 may flow into plus terminal also or minus terminal, and the remaining I2 will be flowing to the other terminal. There is no fixing about this. It depends on how the sizes of the transistor are changed and many other factors, temperature and all, many other factors. Okay, so if you solve this, this is two linear equation. You can solve it easily. Your I1 will come out to be 87.5 nanoampere, and your I2 you will come out to it will come out to be 72.5 nanoampere. Okay. So now you get your I1 and I2. Now what? How to go about this? Read this statement very carefully. The op-amp is ideal except for an input bias current. That means I do not need to consider any offset voltage here, right? So that means I can assume this potential to be present here also, virtual ground condition, right? So this is my grounded now. So how will KCL at this node look like? 0 minus this will be shorted, this will be open, because just let me blow it up and show you. Okay, you see that this will be grounded because virtual short is valid, as no in offset voltage we have to consider, right? This is grounded, this is grounded. That means no current flows through this branch. This current will be nothing but this current, right? So if I use KCL at this node, if I use KCL at this node, how the KCL will look like? KCL equations. Uh, so your KCL equation will look like that your I1 will be equal to V naught by 20. This minus this voltage by this 20, this current will be flowing entirely into the minus terminal. Okay, this is one thing we have got. And another thing is this I2 has no significance. Now we need to find out what is the worst case magnitude, right? So you see your V0 is nothing but 20 into current flowing into the minus terminal. It can be this case 1, right? This is your I0. And another case would be that your I2 is flowing into the minus terminal. Okay. So what is the worst case V0 value? The worst case V0 value will be, one case it is 20 into 72.5. That is your, this will be 1.45 millivolt. Another case it will be 1 point, but it is 187.5 into 20, right? It will be 1.75 millivolt. Now what is the worst case? I did not apply any potential difference between them, so I would expect my V0 to be 0, right? It is an, see, my with these terminals I were supposed to put some VI, right? My VI is 0, so an ideal amplifier should have output is also 0. But now, due to the input bias currents, I have potential developed at the output when my input is 0. So what is the worst case? Which is more deviated from the expected case. Expected is 0. One case I have 1.45 millivolt, other case I have 1.75 millivolt. So the worst difference is 1.75 millivolt, right? So your 1.75 millivolt is the worst case. This is your worst case. Worst case means more deviated than expected. Okay. And what is expected? Expected is your zero input should lead to zero output. Okay. So this is your worst case. This is how you analyze the input bias current condition case. Similarly, problem number 14. Here it is mentioned that the op-amp is ideal except for an offset voltage of 5 millivolt. So what is V0, right? Again, the difference between, let's say this is Vx1, this is Vx2. So Vx1 minus Vx2 is plus minus 5 millivolt or minus plus. You can take anything. Okay. What is your Vx2? The circuit is ideal may accept this VOS or offset voltage. That means no current is going through. That means this is there no current flowing through this branch. Or you can simply say, if no current is flowing through this, you can consider as to be grounded. That this ground terminal is simply connected to this, right? So at Vx2 0 volt, say, then your Vx1 would be plus minus 5 volt, 5 millivolt. Again, we analyze the circuit in the similar manner. Earlier, we have already analyzed this circuit, considering this point to be 5 millivolt plus minus 5 millivolt. What was the answer? Answer was plus minus 61 millivolt, right? So here also your answer would be plus minus 61 millivolt. Same analysis as problem number 12. Okay. So, okay, this problem, let's say solution will be posted. I will not discuss this because time is almost over. Okay. So I can spare 5 more minutes. If you have any query regarding today's session or any doubt, you can ask. Again, I will go through what are the topics we have discussed today. Basically, ideal op-amp circuits. First, we have seen how the tolerance of the resistances affect the output voltage. And we have also discussed why this is required, because we need to know how my output voltage changes, because this will be feeding onto some load, right? Some input to some next stage. It may be some circuit also, some equipment also. So that is why we need it. Okay. The most usage of this this op-amp circuits, or you can see it as differential amplifiers or difference amplifiers. These are very important circuits and used everywhere, right? In every equipment you see, every analog IC circuits, differential amplifier or difference amplifier or op amps will be used. Okay. So then next we have discussed how to go about these integrator circuits. I have told you that there are 3 or 4 methods how it can be solved. I have analyzed one method which is not mostly popular, and also you may not find it in books. So that's why I thought out to do it graphically. So this was the problem. And after that we have taken up again the same problem, but here we are finding out the resistance R at the input. Then we have discussed this difference amplifier, ideal difference amplifier, and how to go about solving this problem. How to, but just by looking at the topology of the circuit, to tell the gain of the stage. Then we have used this improved differential amplifier, or sometimes it is called instrumentation amplifier also. So the purpose behind using this circuit is that two things, twofolded. One is the input resistance here is you looking is infinite, which you are not getting in this case, in this difference amplifier. So you are going in for the improved differential amplifier. Basically, it is nothing but two stages of differential amplifier, right? Again, and another purpose is that you have more handles to get control the gain. Means you have more knobs to play with, or more resistances to play with. You have four resistors to play with, right? Then next we have analyzed another circuit. Then we are discussing about common mode and differential mode. Common mode means any signal can be decomposed into some of a common mode signal and a differential mode signal. So if I apply two input signals, so there will be some common signals, common level of the signals to them, and there will be some differential nature of the signal. So I want the differential nature to get amplified. That is why I use op-amp or difference amplifiers, right? So I want the common mode gain to be ideally zero. So this is how we have discussed this. We have discussed why if I, for an ideal difference amplifier, if I use common mode, then I should have a common mode gain of zero, or the zero output, right? Then we have checked if any of the resistances have any tolerances, then I may not get ideal common mode rejection, right? Or common mode gain zero. Then again, we have discussed this CMRR. CMRR is nothing but your ratio of differential gain over common mode gain. So CMRR should be infinity for a differential amplifier, right? Because your common mode gain is to be zero. for an ideal difference amplifier. Then your I have told you about some definitions in dB. dB is nothing but logarithmic scale, and it is considered taken as a base 10 of log, and also it is a ratio, it is taken on the ratio of the voltage gain, voltages or voltage gain, or power ratio or power gain. For power gain, we will always take 10 log 10, 10 log base 10 of the gain, and for voltage gain in dB, we will take 20 log 10 of the voltage gain, right? Then I have told you a very important parameter of dBm. dBm is nothing but a way to represent power levels. So it is considered based upon 1 milliwatt power, or in reference to 1 milliwatt power. So dBm, always remember that if somebody tells you that I want this much dBm of power, you can convert it back to any value of milliwatt, right? So again, then problem number 12, we have discussed what is this ideal this deviation from the idealness of the this op-amps. One is your offset voltage, and how does this offset voltage come from? This offset voltage come from the mismatch in the transistors of the two branches of the differential pair, right? I have shown you one one two-stage op-amp circuit, how it looks like actually inside this triangular amplifier symbol which you are using, and that is pretty complicated, but not that so. You will in later courses, if you are interested, like Professor Aniruddhan from IIT Madras is taking analog IC design. In those courses, in those advanced courses or PG courses, you will be able to learn about those, how to design and what are the constraints you need to play with, right? So again, we have discussed about this bias current. This bias current problem is coming from that the input you will apply at the base of the BJT, right? So at the base of the BJT, there will have some base current, right? Which will control the operation of the BJT. So that's why this phenomena of offset bias current or input base current issue is there in the BJT circuits, and this will not be that much prominent or almost not present in the MOSFET based circuits, because there the input is applied at the gate, and at the gate you have a silicon dioxide insulator, right? So there no current flows through the gate, right? So that's why this problem will not be there in the MOSFET. This you will remember, right? So even whenever somebody is telling you that IB or offset base current is there, one conclusion you can draw that this op-amp is made out of BJT based circuits, right? Then we have discussed again how to analyze this circuit, and then one problem I have left, I will post the solution. This is similar kind to this 11, 14, 13, and 12, right? This is simply talking about this base current analysis on this same circuit of problem number 14. Okay, so that's all for today. Thank you for participating or attending the session. If you have any query, you can post it in the Ask a Question tab on the course web page, or you can simply comment on the YouTube channel, or you can simply mail me. Okay, so thank you. Let me end the session here.